Hello team! Welcome to another video guide, this one for Programming Assignment 4, the Type Checker or Semantic Analyzer. Since we've already seen the Programming Assignment 4 checkpoint, this video guide is going to start with the OCaml code we had at the end of the checkpoint. But we're going to introduce static types in COOL and then annotate expressions, like in the abstract syntax tree, with those static types. In order to do type checking, we're going to maintain an environment that maps object identifiers to types. We're going to handle type checking 4 different kinds of expressions: integer literals, plus, let with no initializer, and variable references. And we're going to show a few example errors. This time there won't be a submission demo because getting all the way to submission requires quite a bit of boilerplate serialization code to spit out the imp map and the class map and all of that, which is not an instructive use of your time, especially since you've seen how to do it in previous assignments. So let's get down to the heart of it. I have our main.ml file from the previous checkpoint video guide, but I have also created 3 cool programs that are incorrect, that do not type check, that we're going to sort of go over and show off in this video guide. Let's just pull up all of those in a row. Here's our first such program. It's got a class main and a main method. This is mostly so that COOL itself can warn us about it. But we're declaring this variable x to have type string, and we're going to put in a 5. And this just doesn't work. Integer is not a subtype of string, so we'll want our type checker to notice that. Here, I've split this up across multiple lines just for visual convenience, but let's make it look a little bit better. X is supposed to be a string, but we have this local variable y, which is an integer, and then we return y. So this is going to be an integer, in particular the integer 0. So this shouldn't work. But in order to reason about it, we're going to need to keep track of the types of local variables, like y. And then finally, here we've got x, which is an integer. We have another y, which is a local variable, a string. Pardon me. And we add 2 to y. And this shouldn't work. Our typing rule for addition requires that you add 2 integers. And I have this split across, 10 different lines or whatnot, so that we can be super sure that we're reporting the error on the right line number, exactly the same line that COOL is reporting the error on. So let's go try it out. For each of these, we could try to parse bad init 2, and bad plus. And for real testing, you'd want some sort of shell script or makefile. And then we could try to type check. And there's an error on line 3. Int doesn't conform. There's another error on line 3. And this time there's an error on line 7 where the plus is. All right, so we want to get to this. This is our goal. Let's pull up our old code at the end of the static analyzer checkpoint. And this time, this is the full semantic analyzer. And one of the first things we need to do for PA4 proper, we need a notion of a static type. We could just call it type, but type is already a keyword, so I'm going to call it static type so that OCaml is happy with that. And it turns out that a type in COOL is either a class, right? So this is like int or object. These are the things we're expecting. Or the mysterious self-type, which we're not going to cover in any detail in this video guide, but I want to add here because you'll want it eventually. You want to be able to reason about programs that mention self-type. So I'm going to put it here to show you where it would go. Once we've made this new, right, so this is the static type of a COOL expression. Right. Let's have a little procedure that can print these out. If it's just a class like X, and if it's self-type C, for now we'll just return self-type. So we want a way to print it out. And there are some operations that we want to perform on this data type. For example, we might want to know if T1 is a subtype of T2, right? And we write this with this symbol, right? This is subtyping, the Liskov substitution principle. Right? So just as an example, int is a subtype of object, and string is a subtype of string. And if we have, the mysterious color point, if we define, if color point inherits from point, that sort of thing. So how are we going to reason about these? Well, let's check and see what both of them are. We'll check type 1 and type 2, and if they're both cool classes like x and y, well, in the particular case where x equals y, this is like string is a subtype of string, then that is a subtype. And if you're trying to check and see if something is a subtype of object, in cool, that's always true. But for other classes, like just a general class X and a class Y, I don't know what to do here. I should look up in the class notes what the rule is for checking this. Here's the hint. Check the parent map, right? But for now, we'll just say false. And then similarly, if this is anything else, like self-type, check the class notes, we will just say false. All right, so our is subtype is not complete, but this is pretty good. We're handling 2 of the 8 cases. So now we've added these new OCaml abstract data types to represent cool static types. So now we want to go down to our, this is our cool AST, right? And let's stop looking at features. And here's where we're handling expressions. And this is the new bit. We want to leave room to annotate the expression with its static type. We don't know the type at the start, but we will discover it by type checking. So it will be, it doesn't have to be, but this is convenient in OCaml. It will be mutable because it's going to start out as something, and then after type checking, it'll be something else. So I'm going to use a structure type in OCaml. Previously, this was a tuple, but let's just show it off. An expression has a location field, and it has our expression kind field, but now I also want it to have a static type field, and I'm going to make this one mutable, and all of the others are read-only, so this can change. And in addition, because it might not have a type at the beginning, rather than using like null to mean it doesn't have a type yet, in OCaml and Haskell we'd use the option type. So we use none instead. So this is like a special structure with 3 fields, all the stuff we had before, the location and the expression kind, but now we've left room, this mutable third field that's going to start out as none, but in the process of type checking, we'll fill it out. So expression kind, we're going to want a few more of these. There's an integer, there's a plus of 2 expressions, right? E1 plus E2. There's an identifier, all right, of ID. This is just a variable reference, like X. And we're going to allow a special, a single simple let, which I will just call let for now, that has an identifier, a type. All right. There's an initializer option, and there's the let body. This is like let x have t get e1 in e2, where these things, x, t, e1, and e2, these are the 4 parts. Right? The first identifier is x, the second one is t, the expression option is the optional initializer e1, and this is e2. And these are the 4 kinds of expressions that we're going to show type checking today. And because we have this little wrapper where every expression has its expression kind, but also a location and a type, we don't have to mention the type annotations or the locations down here. Every expression node in our AST gets one. Right? So every expression node in our AST has this mutable static type annotation, which we will fill in by doing the type checking. This is a big part of PA4. All right. So now as we're reading in the input, this is unchanged from before. We're eventually going to get down to read expression. And when we are making an expression, now instead of being a tuple, I'm just going to pull it up here in this other window, it's a structure with 3 fields. So the location is eloc, the expression kind is ekind, and initially the static type is none. We have not annotated it yet. While we're here, if we read in a plus, then let's close this. E1 is read an expression and E2 is read an expression, and we return plus E1, E2. If we see an identifier, then the ID is read ID, and this becomes identifier of ID. And if we see let, this is a little complicated. Let's go and see if we can find programming assignment 3 to tell us how we write out let. Output the line number, output let, then output a binding list. For simplicity, I'm only going to consider one binding. We currently only consider one let binding. So, number of bindings, we would read a line, but we're just going to force it to be 1 regardless. And then we either write let binding no init, and then the variable and the identifier, and this is the only one I'm going to consider for now. Again, this is a simplification. Just for this video, I'm just not going to do the full thing. So let binding no init. All right. This is probably what the user would write directly. But now we have the let variable, which is an identifier, and we have the let type, which is another identifier. And now we can say, oh, we want the let variable, the let type, there's no initializer, and in all cases, finally output the body. All right. So here is us reading in a single let only. Now, of course, this code doesn't work if you have multiple let bindings, but that's something you can work out in a bit. So we've read in all of our complicated expressions. This stuff is unchanged from programming assignment 4C. And now we'd want to omit the class map, all of this other stuff. But when we get down to the point where we're emitting expressions, let's go find that. Currently, we print out the location and then the expression kind. But in programming assignment 4, there's a slight change. After the location, you now output the type and then a new line. So right here, when we have one of these expressions, it's going to be an expression E. It's no longer a tuple. This is E's. We'll just pull up what our expressions look like. This is E.lock, and then we're going to take a look at what E's static type is. And then after that, we can take a look at E's expression kind. Have to fill those out in a bit later. One possibility is that its static type is none, which means we haven't annotated it. This should never happen. This is like we forgot to do type checking somehow. That should not happen. Or it can be some class C. which point we output the name of that class, or it can be some self-type C, at which point you fix this, figure out what you should write for self-type. That's left as an exercise to the reader. But this bit here, this is new for PA4. We are outputting the type annotation in our annotated AST. This is it. This is the big change. Right after the location, you output the type. That's it. So now we've just essentially made this promise to ourselves. Like, we are going to fill in this static type field, this mutable static type field, which starts out as none. All right. So let's see how it goes. But we've been writing a lot of OCaml code, and let's just fix up any type errors we have. So OCaml main.ml. All right. And actually, our code works fine. All right. Well, it compiles fine. It's not going to work correctly. Let's just recheck. When we ask cool to type check, bad init1 CLAST, says int does not conform to string. What happens when we run main on bad init1 CLAST? Oh, did we forget to do type checking? Yeah, actually, we forgot to do type checking. So somewhere before we start emitting the CL type, after we're done with this error checking, right? This is the time to do expression type checking. This is the heart of PA4. And how are we going to do it? Well, we want to iterate over every class, then over every feature, then type check the expressions in that feature. What's the plan? Before we get to this iteration, we will want to be able to type check expressions. And typically, we call the procedure that does that type check, or TC, because we'll be writing it a lot. But I'll write out type check. And you'd think, oh, I will just take in an expression, right, type exp, and this whole thing returns a static type. This is how our type checker works. But we're actually going to implement our expression type checker. Right? We implement our expression type checking procedure by reading the typing rules from the CRM or the class notes. So we will want to have the cool reference manual, and these are the typing rules. Let's go see if we can find a common one. Like, do we have that plus rule? Do we not have the plus rule? We do all of our, here's the let rule. That one's going to be a bit more complicated. We've got loop and new. Here's the arith rule. This is our rule for plus. To type check E1 plus E2, you type check E1 and it must be an integer. You type check E2 and it must be an integer. And then the final result is an integer. We read these rules and they become our code. This is the trick. Every line in a typing rule corresponds to a line in your type checking code. So, notice that type checking takes 3 arguments: OMC, objects, methods, and the current class. For now, we'll just need O, our object environment. All right. Fix me MC. It's left for you. But we don't have anything like this object environment. What's it supposed to do? Well, if we follow the class notes or if we read the cool reference manual, we see that the object environment, all right, it's a mapping from object identifiers, names, to types. I'm going to use a hash table for that. We could use a purely functional applicative map data structure based on trees. Let's use a hash table. And in a hash table, you mention in OCaml, you mention the keys first. So an object identifier for us, a name is like a string. And a type is a static type. And this is going to be hash table. our object environment is going to be a hash table. And indeed, we can even have an empty object environment. 255 is a reasonable size. They grow automatically. Right. So with our object environment out of the way, right, or at least defined, we can now start talking about how to type check expressions. Right. Well, this depends on what the kind of the expression is. We have three. It could be an integer of I. It could be a plus of E1, E2. It could be an identifier, like a variable v. Or it could be a let x have type t, and for us, we'll only consider no initializers, and here's the let body. Okay. The goal of doing this type checking is to figure out what the static type is. Once we have it, we can annotate the AST with the newfound static type. It goes like this. Expression static type gets, this is the assignment statement in OCaml. It allows you to write to mutable fields. Some static type. Remember, we were using, recall, none means haven't done it yet, so some means we did it. And then after that stateful update, we'll just return that static type as well. So this type check expression procedure, you're going to end up having, 50 branches here, one for every kind of cool expression. For integers, right, what's the type of every integer constant? Well, if we go back up, true, false, when I is any integer constant, it doesn't actually matter what it is, we return I is int. So we'd be tempted to just return int here. But remember that for us, a type is either class or self-type. So this isn't just int, it's the class int. Right? And now for plus, I want to show off how our typing rules map exactly to OCaml or Python or Ruby or whatever you're doing. I'm going to write out our typing rule for plus in a little comment. Right? Goes OMC, but I'll just do O. E1 plus E2 has type int. If I can prove that E1 has type int, and I can prove that E2 has type int. This is a very simplified ASCII art version of our typing rule. Right? And I'm just going to sort of label each of these. This is line 1, this is line 2, and this is line 3. And we want to recall this symbol, the turnstile, means do type checking. Okay. So this first line, line 1, right, we want to type check E1 using O. So we're going to call ourselves recursively using O to type check this sub-expression E1. That's going to return a type. Let's call that T1. But rule 1 also says it can't just be any type T1. It has to be int. So we'd like to say something like, let's just assert that T1 has to be class int. But we can't just do assertions. We have to report error messages. So if T1 is not equal to class int, right, then it's time to start printing out. Right, let's go see what some of our other error messages look like. Where did we have them? Totally can't find them. This is me not finding them. There we go. Error, %s, type check, adding foo instead of int. You can make up your own error messages. So the first thing I have to do is figure out what line should I report. Do I report it on expression? Do I report it on E1 or E2? Well, let's go take a look at the page for programming assignment 4, and it tells you what to emit for each one. So unknown actual arguments, location of block, while, if, case expression, line numbers on error to be reported. Do they have arithmetic? All right. So errors with types of arguments in arithmetic, the location of the arithmetic expression. So the arithmetic expression is exp, and its location, well, actually, we stored that in a convenient field. We called it lock. So this would be expression.lock. And the type we got was T1. And then if this happens, we will want to exit the program and not emit the class map and the annotated AST and all that jazz. Now we're going to do the same thing and type check T2 for E2. This is line 2 in our typing rule. If both of these work, line 3 in our typing rule, we return the final type, class int. I'm going to rewrite this typing rule one other way, which may make it a little easier for you to see what's going on. If you like, this rule really says type check E1 and get T1, but T1 must be int. Then type check E2 and get T2, but T2 must be int. Then your return type is int, so return it. And basically, the heart of programming assignment 4 is that you take every one of these typing rules and you break it down. So this one with dispatch, instead of being 1, 2, 3, it's going to have like 7 parts, right? It goes on forever. But each one of these becomes a line of code, right? This is just you recursively type checking E0 and getting type T0. And so the rules may look daunting, but every line in the formal typing rule tells you exactly what code to write. Whenever you see this type check, this means make a recursive call. And that's how you do it. So we've written a bit of OCaml code. Right? Let's go see if this code compiles. All right. Pattern matching is not exhaustive, not exhaustive. Yeah, totally not exhaustive because we're not handling all of cool. Right. So we've handled integers and plus, but we have not yet handled identifiers and let. Well, our rule for identifier should be that we look it up in O. If O of ID equals T, then that's what we return. But remember that we have to think of the failure cases as well. So here's V's location and here's V's name. If we look up in O V's name and we find it, then this is good. But there's also the possibility that when we go to look it up, it just hasn't been declared at all. That would be bad. That's a type error. So here, we may be in V location. We say undeclared variable S. And you have to figure out which location do I want, this one or some other one. But if it works, then we'll just actually do this. So this in mem is membership check, returns Boolean in OCaml, and this does the actual lookup. Okay. So if we've put all of our variables into our convenient hash table, then looking up identifiers is going to be totally fine. But where do we put those variables into our hash table? Well, one big place is when you encounter a new let. So here's the variable location and the variable name. Here's the type location and the type name. And what we want to do is add to our object environment that now this variable name maps to, and for now we'll just do class of type name, fix me self-type, I don't know, but maps to this class. Now we'll want to remove it later because when it goes out of scope it shouldn't be there anymore. So we always want to pair these up. After we've added vname to O, we want to remove it later. But while it's still in there, we can call ourselves recursively and type check the let body. While so this part is add vname to O, add it to the current scope. We type check the let body with the bound variable added to the object environment. Where am I getting this stuff? Well, this is the rule for let with no init. We're ignoring all this stuff about self-type, which you can read up on later. But here, this was our notation for extend O with X having that type check the let body, and whatever type T1 it returns, that's what you return. So we're just going to return the body type. Let's see how well we're doing at type checking. All right, so this is pretty good, but we made this type checking procedure, but we never actually call it. We never use it. You can even see OCaml yelling at us about that. It says you never use type check. Right? So after we've done all of that, now we iterate over every class and type check all features. So I'm just going to find some code we had above that was iterating over the AST and steal it. All right. So we're iterating over a particular class. It's got some inheritance. We probably don't care about the inheritance now, but we do care about the features. So for every one of the features, we're going to take a look and see what it is. And for us, there are two possibilities. A feature is either an attribute of identifier, type, and some init, or it's a method. And for now, we're just not going to type check methods. Fix me. But I am interested in type checking attributes with initializer expressions. Right, so we'll leave all the rest of the options undone for now. But when we encounter one of these attribute initializers, recall this is going to be something like x is an integer gets 5 plus 3. Something like that. This is the initializer. We want to type check and make sure not only that 5 plus 3 type checks, but that it conforms to int. Right? So the initializer type is going to be, when we type check, this is the initializer expression. The initializer expression. This means we need some object environment O. Oh man, I don't know what that should be. For now, let's use an empty object environment. This is wrong. You can see in the cool reference manual that you'll want to add all of the features, including potentially inherited ones, to the object environment before you start type checking. But for now, we won't do that. We'll just do an empty object environment, and you can add in more later. Okay. Fix me. Add features to object environment. But if we have this initial type, now what we need to do is make sure, conceptually, we want to assert that this type is a subtype of, this is the, let's call this the like declared type. Okay. That if you said you were going to give me an integer, you actually did. Well, our way of checking that was called isSubtype. So if the initializer type is a subtype of, and we'd like to say declared type, but this is actually one of those identifiers. This is the declared type location, and this is a declared type as a string. So just assume they did not say self-type. More on that later, right? Check for self-type. But if it is a subtype, then we are happy. This is so awesome. Everything worked out. But if not, then it is the kiss of death. And we need to go back and find our print stuff. And when we're type checking, we had a, initializer for blah was blah, not blah, something like that. So we're going to need to fill in a bunch of those. The first thing we need to do is figure out what location we should report the error on. So we go back to not programming assignment 3, but programming assignment 4. Parameter list method, inheritance cycle, inheritance type problem, redefining a formal, other attribute problems, attribute location. Attribute initializer does not conform. Attribute name location. All right, so this was the name lock and then the name. So we're supposed to print out the name location because it told us to. And this is the initializer for name. And the type we got was the initializer type. And that didn't match the, is not, blah, did not match declared blah. And then we exit. So let's see if this stuff compiles. All right, seems to be compiling so far. Let's see how close we are to matching. Look, we're doing pretty well. The only thing we actually check is whether we got the error on the right line. But for the purposes of debugging, seeing what the error message is helps quite a bit. So it says, int does not conform to string. And down here, we say, oh, the initializer for x was int, which did not match the declared, did not conform to string. So we're getting the first one right. All right. And once again, this says int does not conform to string. And this says the initializer was int, but it did not match declared string. But now, for big bucks and no whammies, let's try this bad plus. And it says on line 7, arithmetic on int string instead of ints. And we also say on line 7, adding string instead of int. That's pretty much it. So let's just go back and take a look at where we were actually printing out that line 7. That's one of these, where either type 1 or type 2 was not an integer. So let's go back and actually change one of these, like bad plus. Let's call this undecvar. And here, what if we change this y to a z? And you notice this is not declared. Oh gosh, I can't spell. And we got this variable z on line 9 that's not declared. Hopefully, our code will correctly yell at us for this because we're maintaining an object environment. Unbound identifier, and we say undeclared variable. Excellent. So we're catching a number of the type checking errors, and what you would do for programming assignment 4 is essentially exhaustively go down this list and handle all of them, and then emit the class map, the implementation map, the parent map, and the annotated AST. And the only real difference in the annotated AST is you print out the type before every expression, and also you may have to print out these internal expressions. But we started with programming assignment 4C video guide code. We introduced static types. We added expression type annotations, which started out as none, but we changed them to some. We introduced a simple environment mapping objects to types, and we extended it with let. We showed how to do int plus let and variable identifier references. And we caught a bunch of example errors. And that's it for this video.